A apărut.
A apărut. Bună seara, dragi prieteni! În mod normal vă așteptați ca să ne începem live-urile cu Ada Rosetti și cu Ciprian Mihali. Încă nu ne-am hotărât ce să facem, așa că am zis, dacă tot este, să facem așa o mică încălzire. Și în seara asta o să vorbim despre fizică. Îl am invitat aici pe Horațiu Năstase, care este cercetător și profesor la Paulo în Brazilia. Bună seara!
Bună seara!
Am vorbit cu Horațiu și în esență o să vorbim în limba engleză. Horațiu este de foarte mult timp în Brazilia, n-a mai fost în România de mult timp și este foarte cunoscut în domeniul lui. O să-ți fac o mică introducere, Horațiu, dacă e ok.
Mulțumesc.
Iar după aceea o să continuăm în engleză, pentru că el scrie foarte mult în limba engleză. Am aici, ca să încep totuși, Horațiu, cu chestia asta, am aici câteva din cărțile pe care...
One of the components of the proton in the nucleus of an atom. All of these things are just, to us they appear different, but in reality they are just different modes of vibration of a very, very, very tiny string. So imagine that, well, that you have, let's say, a violin string, right? You excite it, there are different modes of vibration that corresponds to the different sounds that we hear. And this being a fundamental string, its different modes of vibration correspond to different kinds of particles. So the hope was to describe everything in nature, all kinds of particles, and the forces that act between them. All of these to describe as just the result of tiny little vibrating strings. So the idea sounds simple, but the mathematics of it turns out to be very difficult. So
very complex indeed.
Very complex.
I will just ask people because they say that the live has a problem.
Okay.
Cu alte cuvinte, se blochează live-ul. Nu știu de ce, pentru că la mine aici funcționează. Do you have a problem, Horațiu? No,
no, for me it's fine. I don't know.
Okay, and so I think it's really coming from StreamYard. I don't have any problem. My internet is good. The internet of Horațiu is good. So I don't know what is happening. Why would you get a live? Can you a live problem? Can you describe the problem in comments? What is happening? Is still happening? Some people say that that it is working.
Yeah.
I think let's continue.
All right.
Some people say they don't understand anything. Now it's okay. Yeah, I don't know. The point is the following. We can continue and then see what is happening, because otherwise we also have here the recording. So we can play back the recording later on the YouTube channel. Okay, so let's continue. Now I see, for example, that some people say it is okay. Like, funcționează bine, bună seara. It is okay now. Look. Okay, let's continue. So the point is that every particle is made of small strings. But then the question is, what kind of material? From what kind of material are the strings made?
Yeah, I mean that's the thing. It's not a material in itself. There's no material. There's nothing more fundamental. So if you cut the string, you don't obtain two half strings. You would obtain two strings that are identical to the original one. So you have to think of them as fundamental in the same way as you think of a point particle as fundamental. You don't say that it has subunits. Well, it's easy to understand because it's kind of a point and it's hard to see how you could break a point in two. For strings, you might say, well, maybe I cut it in two. But it's the same idea that these objects are fundamental. There's nothing smaller or more fundamental than them.
So I would say that's a beautiful playground for geometry, because you may look at it like a fundamental geometrical object and then try to play with it.
That is absolutely correct. So in fact, the one of the interesting things about string theory, it hasn't contributed for the moment too much towards practical physics, but it has contributed a lot towards mathematics. And one of the ways it has contributed is by introducing the concepts defined as quantum or stringy geometry, where it's the geometry that is felt by strings rather than by particles. And that has the extra feature that sometimes something looks singular for particles, like you look like a tip of a cone, but it might be smooth for strings. So, it is a beautiful playground, and a lot of very interesting mathematics has resulted from it.
So then the question is, how did you come to study strings? Can you tell us a little bit about your background and your professional, let's say, career?
Sure. I mean, I started my undergraduate at Bucharest University, and there nobody knew about strings at the time. At the time, nobody had even heard the word string theory.
But it was in the beginning of 90s, I suppose.
Bucharest University. But I went to, and myself, I just heard it in some science fiction show. But I went to Copenhagen University, to the Niels Bohr Institute, where Niels Bohr developed the theory of the atom beginning of the 20th century. And there I was introduced by one of the professors. He said, well, look, there's this beautiful theory called string theory. Are you interested in studying it? And I said, yes, it sounds very, very interesting. And that was the beginning. And I also had the luck, really, to start when there was the so-called second superstring revolution, meaning string theory was very exciting at the end of the 80s. Then the excitement kind of ebbed down and started again just about when I was starting to study it. So yeah, then from Copenhagen, I moved on to the US for my PhD at Stony Brook with Peter van Nieuwenhuizen, who was one of the discoverers of supergravity. That's a theory that is, the first step towards string theory, let me call it this way. So it started slightly before it. And then, I continued in string theory. I was in Princeton, Brown University, and Tokyo Tech in Japan.
And this is one of the book which you wrote, Introduction to the ADS CFT Correspondence. And when I saw it, I said to myself, wow, there's really something to understand what ADS CFT is, and to write about it, and even to collaborate together with Juan Maldacena, who was one of the founders of this ADS CFT correspondence. So let's dive deep a little bit here to talk about a little bit about this. So string theory, that means that particles are made out of strings. Or maybe we go back to the idea of the quantum gravity, because as I remember, string theory was very popular because they said at one point, like Brian Greene told us in his talks, that string theory can be a theory of everything. That means it can unite quantum mechanics and gravity. So that in that way it could be a quantum gravity theory, the theory of everything. So maybe let's discuss about that. Why would string theory be a quantum of everything or theory of everything? and then dive deep into the ADS CFT correspondence.
That's right. So string theory, as I said, is a theory of the vibrational modes of a string. And if you look at the vibrational modes of the string, you realize that one of the possible vibrational modes, one that is that requires very little energy, we say that it's a massless vibrational mode, is a mode that has the symmetry of a quadrupole, which is the same symmetry that one finds for a gravitational fluctuation. So that's why we say that the quantum of this gravitational fluctuation, the graviton, is one of the modes of the string, and therefore gravity itself, or more precisely a quantum version of the classical gravity that we see, is embedded into string theory, is part of string theory. And that was something that was very difficult to obtain. So whenever people tried to make a quantum theory of Einstein's general relativity, they run into unsolvable infinities, things that messed up the calculations, and people thought that there's no way around it, until came string theory and showed that if you make this graviton as just one tiny part of all the other possible particles that are strings, then the quantum theory of gravity makes sense. There's no infinities in it, and looks nice. It's still very hard to calculate, but at least fundamentally there is no problem. So we say that string theory is a theory that unifies everything, including gravity, into a quantum setting.
And then came ADS CFT correspondence, which at that time was a very, very big hype, in a sense that here there is a model in which it may work, or not.
That's right. So the ADS CFT correspondence now changes a little bit the perspective. So while string theory, as I said, started as a theory trying to explain, very, very high goal, to trying to explain everything in nature, to try to explain all the particles and all the interactions. Now, and from that point of view, the goal, we haven't reached that goal. It's still elusive. But now comes a more precise goal, which is, let's try to describe, to make calculations in theories that we fundamentally understand, but that are very difficult to calculate with, such as the theory of quarks and gluons, that is the theory of the strong interactions between particles, the strong nuclear forces. Now, so for this theory, we have a mathematical structure. We have what we call a Lagrangian for this theory. And in principle, we could do everything. It's just that in practice, we cannot. It's extremely complicated. And the goal of the ADS CFT correspondence that was started by Juan Maldacena is to say that there is a sort of duality, so two different kinds of descriptions for the same thing. On one hand, we have the standard description for a quantum field theory, like this theory of strong interactions. And on the other hand, we have a gravitational description in terms of string theory and its gravity part. And these descriptions that formally look very, very different, they're actually the same. They're two different points of view to look at the same thing. So, but the plus then is that in one description, something looks hard, then in the other description, the same thing looks very simple. So things are very hard to calculate in the QCD, in the theory of strong interactions. The same things are very easy to calculate in the gravitational theory, in the string theory, and vice versa. Something that is very simple in the strong interactions becomes very complicated in the gravity theory. And so one of the properties of this duality, of this relation, is that it looks holographic, meaning it's the same kind of relation as one obtains when one looks at a hologram. So a hologram, what is a hologram? A regular hologram. It's a two-dimensional photograph, right? That when we look at it, we see a three-dimensional object. So how does that happen, right? On one hand, the object, the hologram itself is two-dimensional. On the other hand, we see three-dimensional information on it. The way this is possible is because the mapping between the three-dimensional object and the two-dimensional hologram is very non-local. So one point on the hologram corresponds to all the points in the three-dimensional objects, and vice versa. One point in the three-dimensional object corresponds to all the points on the hologram. You can do a very simple experiment with that. Well, if you have a hologram that you don't mind destroying, if you cut it in two, you take a small hologram, you cut it in two, then what you obtain are not two halves of hologram like you would obtain with a regular photograph, but you obtain two holograms of the same object, just of lower quality. That shows that the mapping is non-local in nature, is not local like in a normal photograph. So the same kind of mapping is this ADS-CFT correspondence between a field theory and a gravitational theory. So the gravitational theory is the analog of the three-dimensional object, and the field theory the analog of the two-dimensional hologram.
And this was a hope at that point. Maybe we discuss about one more thing about the book which you wrote, String Theory Method for Condensed Matter Physics, and then we discuss about the problems of string theory, the question that people have, what happened, and then why we don't have it yet, and also about the experiments. And then also we take questions from the audience. So I would like the audience to ask questions in Romanian. We will read in Romanian and we will answer. And I know that people ask why we discuss in English. I said in the beginning that Horațiu feels much more comfortable in English because he basically teaches in English, and all these words, he knows them in English, and it's much easier for him. So I try to put the book here, which you have on the screen, String Theory Methods for Condensed Matter Physics. While I put here the book, maybe you explain me, because I did my PhD in condensed matter physics, and I know that in condensed matter physics, okay, I have the particles and I can work with point particles. I can do quantum field theory with point particles in condensed matters. Why would I need string theory in condensed matter physics? So for the people who maybe don't know, the condensed matter physics is, for example, the physics of crystals, where you have the atoms which I ordered and they form different crystals. And because of that, you get all kinds of structures which you want to describe with physics.
Right. So one of the aspects of the ADS-CFT correspondence is that, so as I said, when one side is very easy to describe, the other is very hard, and vice versa. Now, what does that mean in practice? So hard to describe are systems for which the interaction between the components is very strong. So we don't have any handle of how to approximate things. And And that is something that happens very often in condensed matter physics, at least in the systems that people are currently interested in. So their interaction between components are very strong. So if we talk about the crystal, let's say, what I mean is the interaction between electrons. The electrons in the crystal normally, well, crystal or metal more precisely, they would move around throughout the whole system, and they would get the chance to interact with each other. And sure, there are some in which the interaction is small, but the more interesting ones is where the interaction between the electrons is extremely high. And so there's very little handle on how to describe them using standard particles, right? We have to choose a different kind of description to describe all this interacting mess of electrons. And then that's the beauty of ADS-CFT, that it relates something that is strongly interacting with something that's weakly interacting. So we can describe these systems by using some weakly interacting gravitational description, where we can do calculations.
I'm thinking, for example, of strongly correlated electron systems.
That's right. That's exactly right. That's one of the most important applications.
Now,
the only difference, so with respect to the original motivation, as I said, the original motivation was for the description of the strong nuclear force. For the strong nuclear force, there was there's a well-defined description, and we try to get to that by using some precise mapping that we obtain in string theory between gravity and the field theory. But in the case of condensed matter, that is more complicated, because the only thing that we know are the electromagnetic interactions between the electrons, and nothing more fundamental than that. There's nothing more fundamental than that, and that is not enough in order to describe such to derive a description between field theory and gravity. So what one does is sort of another kind of phenomenology, meaning we invent some model, some field theoretical model for the condensed matter, and we define it by fixing some parameters to be something that match experiment, and then the other everything else that is obtained is a prediction. So that's kind of what one means by phenomenological models. And so the applications to condensed matter mostly are within this framework of phenomenological models.
But it's okay, because, for example,
Sure.
when we learn first about the high temperature superconductors or about the low temperature superconductors, even in the low temperature superconductors, you start with some phenomenological model, lambda, and further. And
that's exactly right. So that's what one does anyway, even in normal condensed matter. That's right.
Yeah. And it's very funny, because for us physicists, that's a bad word, phenomenological, in a sense that we have a model, we don't know exactly how it works, but it's good. Yeah. And in philosophy, they usually see it as a very good word, but that's a different thing. I've got here a question related to this from Adrian. Can we perhaps cover new phases of matter or exotic materials with novel properties? I suppose using your model, using, let's say, string theory methods in condensed matter physics.
Yeah, I mean, look, so the problem is in some sense an overabundance. So from string theory, you can have many kind of models. You can describe many kind of phenomenological models, and the question is to have a corresponding material or system, condensed matter system, for which such a phenomenological model could be applied. So that's not always obvious. So we can invent lots of phenomenological models from string theory, and the issue is to see which of them can be applied to particular systems that we're interested in.
Okay, I would say we go back to what happened in the meantime with the string theory. And there are questions here, like, for example, Doreen, the theory of everything is something real to achieve. So let's start from the beginning. The question being, in the last, let's say, 5 years, I would say, maybe even 10 years, but no, certainly 5 years, people don't talk much about string theory. At least in the popularization of science, in the new science articles, we read very, very little about the string theory. And of course, we also have the other books of the opponents of string theory. I have some of them here. Who said and then said, yeah, okay, this is not going to work because of that and because of that. And I personally, for example, I really struggled with some points. For example, I struggled with the fact that you really need to have 10 dimensions, if you talk about superstring theory, yes, in order for everything to fit into place. Or otherwise, as I put it as an experimentalist, otherwise you, for example, get particles which have a very high mass, because you don't get the low vibrations, you get mass Planck, and that's something you don't want to have for fundamental particles. And there are other reasons, for example, the Calabi-Yau spaces, where they said, well, in order to make it work, you have to put it into 10-dimensional space-time, if you talk about superstring. But not only that, you have to do the compactification, because we see only four dimensions. So you have to compactify the other 6 spatial dimension in different ways. And then Calabi-Yau spaces, they provide you many ways. So then people would ask, okay, did you find a way to compactify the strings in order to get the particles which we have right now? So in other words, what happened in these 5 years? Why we don't talk so much about the string theory?
Well, the short answer is just sociology. I mean, it's nothing really new that's happening in string theory. It's just, on one hand, so people unfortunately seem to follow some sort of fashions, and string theory was fashionable for a while. Now it's not. That's basically is not anything more than that, I would say. So most of the criticisms are, have little foundation. The one criticism that it's worth mentioning, I think, is really that we have been doing this for so long, and we are not able yet to obtain one model that describes perfectly what we see. But let me back up a little bit and say, a question about having more dimensions. That was actually a good thing. That is not, well, I mean, you might, depending on your preference, but the point of view that there is a fixed dimension is actually good. So the point of string theory,
you are very specific.
You're very specific. That's right. So the point of string theory was always to give a unique theory. And so the logic that string theory followed was really the logic that was started by Einstein. Einstein discovered his general relativity by thinking about consistency. So it was the first time. So special relativity was based on experiment, but general relativity was not. General relativity was based on consistency. So Einstein just thought, well, we have this special relativity that we've proven is correct, and then now we have gravity. How do we put the two together? And by thinking about the consistency of that, he arrived at general relativity. Now, similarly, for string theory, we try to think of 2 things that we know: quantum mechanics and gravity, and we want to put them together, and we're more or less forced to go towards string theory, at least for weak interactions, for perturbation theory, how we call it, for weak interactions. There's not much else that can be done. So for strong, if you try from the beginning to think of strongly interacting systems, you can have other things, as you mentioned, loop quantum gravity or something else. But in the realm of perturbation theory, there's pretty much it. There's just string theory. And then the issue is the theory has to be unique, just like Einstein found a unique theory of general relativity. And we first find that we have to have 10 dimensions, considering the consistency of quantum mechanics with strings. And then we find that there's a unique theory, meaning there's a unique, number of different particles. So there's not, technically there are 5, but they are interrelated. So in the end, there's basically one unique theory. So I would say the uniqueness of string theory is an asset. And yes, it gives us 10 dimensions, but okay, that is a fact, and it has some advantages. You mentioned Calabi-Yau spaces. So from 10 dimensions to 4 dimensions, the simplest way to go is to consider these 6 dimensions to be compact, something like a sphere, right? So you say that these 6 dimensions are something like a sphere. It's just that they're so tiny that we don't see it. So we cannot move in this other 6 dimensions. They're so tiny. But the extra ingredient, the extra feature that comes with this is that now we have geometry for this space. And geometry is associated with symmetries. Like for the sphere, there's a rotational symmetry, right? We can rotate the sphere and we see it stays the same. And so when we go back to, after compactifying, we obtain the symmetry of the sphere. And so that allows string theory to geometrize symmetries. All the symmetries that they look abstract in particle physics, they look ad hoc and abstract. For people who might have heard it, for the standard model of particle physics is called SU3 cross SU2 cross U1. It's just some symmetry that looks random. But the point is, in string theory, all of these symmetries are geometrical. And so there is a hope that once you find the correct space to compactify, you will see that symmetry as geometrical. But we have not, unfortunately, found yet one answer for one vacuum, so one low energy description of string theory that gives exactly what we see. So.
Yeah, and then you have also the other reproach, or how do you say in English? The fact that, there is no experimental evidence. And I read, actually, I was not aware that you attracted some media attention, let's say about 15 years ago, when you said there is a way to check it experimentally.
Well,
maybe
that was kindly people took my words and twisted them a little bit, but we can talk about that.
You can clarify it right now if you want. I mean, what did you try to say, or what was your approach? And then also going towards the answer, like, okay, why is it so difficult to actually prove it experimentally or get hands on it experimentally?
So the reason why it's so hard to obtain experimentally, it's kind of simple enough to understand. So the weakest force that we know is the gravitational force. Well, it's the one that we mostly observe, but that is only because electromagnetic forces force opposite charges to coalesce, and strong nuclear forces force particles to coalesce, and so on. But the gravitational force is really very weak. So the gravitational force being very, very weak, one way to describe this is that the mass scale at which, or I should say, the energy scale at which they would, the gravitational force would become very strong, is extremely high, and it's about 15 orders of magnitude beyond, so 10 to the 15 times stronger than what we can obtain at current accelerators. And since we say that string theory is a theory of quantum gravity, that's the scale at which we should see new stuff happening. So it's absurdly out of reach. I mean, not now, but even, you know, in the future. There's one something that tells you a little bit the problem. If you would make an accelerator, a circular accelerator, it should be roughly the size of the solar system. So yeah, that's kind of very, very difficult. But so that's why from the beginning we knew that string theory will be very hard to prove experimentally. But ADS-CFT gives an implicit proof, in the sense that now you're just looking at the field theory side, where you know things like this theory of the strong nuclear force, and you make predictions in principle. You can make predictions in principle about the other side, about string theory, and that's roughly where the idea came about the fact that the stuff that came into the newspapers, very wrongly so. But anyway, so what I had said in a small article was that if you describe the collisions that actually are observed at current accelerators, collisions for instance, at the accelerator in Brookhaven, where they collide very heavy ions, and then they obtain a sort of plasma. There's a fireball of this plasma. And I argued that using ADS-CFT, that this description is mapped into one-to-one into a description on the other side of two particles colliding and forming a black hole. And of course, all of that got lost. So I actually gave an interview to New Scientist where they reproduced very correctly what I said, but then people had read the New Scientist article, and they thought it meant something else, and they said, oh, the Brookhaven creates black holes. So, yeah.
And that's a very bad idea for the general public.
That's right. So I even got some scientists complaining to me. I said, I didn't say anything like that. What you're talking about?
That's always very difficult with science popularization. I think this is the book which I didn't dare to say that you wrote, Cosmology. And
that's also me. Yeah.
Yeah. That's also. And what did you put from string theory in cosmology? Is there? Of course, if the string theory is supposed to be a theory of everything, then you'd expect to go into cosmology, because cosmology is the whole cosmos. But is there something specific here which you can address with string theory?
Yes, actually, that's one of the more promising areas of string theory that has some potential relation with experiments. So. So I said it's virtually impossible to build an accelerator that will actually reach these absurdly high energies at which we will see these strings. But the universe had already built it. It's the beginning of the universe. At the beginning of the universe, if you go very, very close to the original Big Bang, the energies are absurdly high. So at the time, the effects of string theory would be very, very important. So the only question is, do those give an imprint into something which we can observe? And there are possibilities. There are some ways, some string theoretical models in which you can give an imprint of some string theory effect onto what we'll observe and is known as the cosmic microwave background radiation. This is a radiation that permeates the cosmos, and well, nowadays people have very fancy TVs, but when I was young, you take a TV with a tube, and if you turn that on and there was also nothing on the TV, just static, about 10% of that static was the cosmic microwave background radiation. So you can actually see it. And so now, unfortunately, it's harder to see. But if you get one of these TVs with
but now we have internet, so I can show a picture.
Right.
Okay. So then we are going to look at the picture here, and then. So
the cosmic microwave background permeates everything, and then. So what is this background radiation? Well, this is formed when the universe cooled to such a point that atoms are formed. And then when atoms are formed, yes, thank you. This is the CMBR. So when atoms are formed, then suddenly photons can pass through atoms. Atoms are, once in a while you see one of them. So you say that this is the moment that the universe became transparent. If you go before that, it was opaque. Now the universe became transparent. And in this, you can find an imprint of small fluctuations at the Big Bang. And these are really sonic fluctuations. Sonic type fluctuations, the same way as you make a sound and you can see the sound making some waves in some iron filings or something like that. So this is really, you can think of it as the sound of the Big Bang being imprinted into the sky. And so in these fluctuations, there's some tiny variations that follow a certain curve. So the CMBR fluctuation curve depends very much on the details of what happened at the beginning of the cosmos. So
you mean the Fourier transform spectra, or what curve?
That's right.
Okay, so, because then I can look for it.
Yeah. So
and in that curve.
So it has a bunch of peaks. It's like a regular decaying oscillation curve. So it has a bunch of peaks that become smaller and smaller, and it's a function of it's a Fourier transform or a function of smaller and smaller angle, if you want. So fitting this curve with something that happened at the beginning of the universe is what is our experimental data about cosmology. That's really the most important experimental data about cosmology, and yeah, string theory can contribute there.
So in other words, you can do a better fit. I try to show it here.
Yeah.
You refer to this curve here, I suppose.
Exactly. That's exactly right. Yeah.
And then we have these particular peaks. So the first one.
So the first one is the most important, but I mean,
tells us that the
actually
universe
this is slightly older. This is slightly older now.
This is Wikipedia.
These error bars are much smaller. So
this is Wikipedia. So
no, sure, because they don't have the rights to put the correct one. So
I see. And then basically you try to get a better fit using string theory. I see that we have like 10 minutes more or less left, and there are some questions here, and so let's take some questions, and also I ask people to put questions, and they can put them in Romanian as well. We discuss in English because it's much easier for Horațiu to talk in English here, these specific terms. Let's try with this one here. Why is the ADS CFT easy in the anti-de Sitter regime? So ADS stands for anti-de Sitter, which is kind of geometry in general relativity, but very much more difficult in the de Sitter one. Is it possible in the de Sitter one? The one that our universe is in. So Rob really knows the stuff.
Yeah, it's actually a very good question. So let me try to explain it first a little bit. So anti-de Sitter space is a space, so a space-time, I should say, that has negative curvature. Now that is, a little bit difficult to picture. So I don't know exactly how to say that.
May I put the Escher drawing? May I put the Escher drawing, which people usually use?
Yeah, okay, that Escher drawing. Yeah, that I'm not sure. That's nice, but it doesn't explain too much.
Oh, okay, then I don't put it.
But anyway, but de Sitter is easier to explain. So de Sitter is a space-time, so with time in it. But if you would think of the Euclidean version of it, this without time, just space, this is just a sphere. So the Sitter would be just like a sphere. So that is positive curvature. Yeah, the sphere is positively curved. So it turns out that our space-time now it has a small so-called cosmological constant, which means is very close to de Sitter. It's not de Sitter, but it's very close to de Sitter. And also perhaps at the beginning of the universe had the de Sitter phase as well. So yeah, why anti-de Sitter? That is actually a very technical question, and it has to do with the fact that the string theory that we're talking about has an extra symmetry called supersymmetry, a symmetry between bosons and fermions, which are something like electrons and photons. And when you consider this supersymmetry, the theory is so symmetric that its its vacuum, its low energy descriptions are very much fixed, and they happen to be anti-de Sitter. So that's what.
That's why it works very well with anti-de Sitter.
So this is just a feature of the fact that we're doing the easiest things first. So in physics, I'm sure you've heard the joke that we're looking for a spherical cow approximation. So we want to describe a cow, but we describe it as a sphere. So anyway, it's just that the first thing to understand, which is the easiest to understand, is this anti-de Sitter in a supersymmetric theory. But in principle, if you would understand things very well, we should be able to describe also de Sitter. And there are attempts at that, but the attempts are still very much debated. It's not very clear cut.
I don't know if it was a very good idea to mention supersymmetry, because Rob continues. He says the following: in string theory, is string theory less and less plausible as we increase the energy in our accelerometer and we don't find supersymmetry, considering that string theory requires supersymmetry. So for the people who don't know, the idea in the beginning was that at a Large Hadron Collider in Geneva, when we have a lot of energies, colliding energies, we will discover supersymmetry. And that would be, let's say, the grounding thing for the string theory, because string theory requires supersymmetry. But it doesn't seem that at Large Hadron Collider we found supersymmetry. And some people argue that the window is closing, in the sense that if you want to discover supersymmetries at larger and larger energies, you have to fit many more things together, and it doesn't look quite natural. I don't know if that argument is correct, but maybe you give your answer to this.
Well, so I hear this a lot, and there are two parts two points that one should raise when explaining this. So the first one is, what does it mean that we didn't find supersymmetry, and so we should forget about supersymmetry? Well, what we didn't find are the most natural, most generic models. So, you know, in experiment, what you do is you have to scan a certain parameter space, and you know, so it's not like you can test all possible theories that you can ever imagine. What you test is you parameterize your ignorance in terms of some parameters and try to vary these parameters. And people have excluded a lot of these theories parameterized by some simple parameters. And so a class of people, which are the ones that think, you know, things should be simple and easy and so on, are already giving up on supersymmetry. But it's also important to realize that string theory, in string theory, things are unique. So when you derive a certain model, there would be a uniquely defined model. It's not like you could vary the parameters. That is the whole point about string theory. And so it's not clear that such a model will be, when it is found, if it's ever found, that it will be something that was excluded by this. It could be that something looks very contrived if you look at it from the generic point of view, but it's actually, you know, coming from string theory, which is very unique and simple. So that's certainly a possibility. And the second possible answer to this is, while string theory is easiest in the presence of supersymmetry, it's actually possible to do a lot of string theory without supersymmetry. It's more complicated, but it's possible. So it's not even excluded. So yeah, I would say really the only thing that the LHC not finding supersymmetry has done is to sort of move people away from string theory as a sociological effect Phenomena. of you know, being out of fashion suddenly. It's not, yeah, it's not really a statement about string theory.
This type of questions, which maybe it's a question of understanding. In string theory, the universe is expanding or is compacting. I think it doesn't have to do with string theory, but you may answer the way.
Well, the universe is always expanding now, right? So close to, you go backwards in time, the universe, it's becoming smaller and smaller. So the universe started in a big bang and then had started to expand. Now, certainly one relevant question is, what happens near the Big Bang? Because as I said, in string theory, geometry is modified somehow, right? So in the original thinking, in terms of particles, you said the universe was a point and then it started exploding. But now you have other possibilities. You have the possibilities that very close to the Big Bang, string geometry was relevant, which smooths out a lot of singularities, as I said. You have also possibilities that was dreamt up even before string theory, so-called cyclic models where the universe undergoes cycles of contraction, expansion. So Big Bang, then Big Crunch, Big Bang, Big Crunch, and so on. So it is certainly possible to consider cyclic universes, the ones that first expand, then collapse, and so on. But the most standard model is where the universe simply expands.
Yeah, let's take one more question, and because there are some of them here, I'll just make a choice. First, I will thank George, because yeah, he basically sometimes repost the things we do here in the Facebook group, Misterele Universului, and that's also good for us, of course. Then Rob has a very difficult question, which I will skip. What do you think about Samir Matur's fuzzy balls theory of black holes? Because that would be so specific that I would have to
answer a lot. So,
yeah. But maybe I will take this question from Rob, and then we finish with this about the dark matter, because people know more or less about dark matter. And Rob says, some people don't believe that dark matter exists. I suppose he thinks of the, how is it called, the modified gravity. But we can see its contribution in the baryonic acoustic oscillation. So the acoustic oscillations you measured after the Big Bang. Does Horațiu think that's a very good evidence for dark matter existing? In other words, is the contribution which we see in the baryonic acoustic oscillation an evidence for dark matter, or there may be something else? Still no evidence for dark matter.
Well, actually, it's not baryonic acoustic oscillations which are the most important constraint on dark matter. So there are models that, so yeah, it's better that I would explain. So dark matter is matter, as the word says, matter that is not luminous, it's dark. So matter that we don't see through its luminous effects, but see through gravitational effects. We only see, let's say, so if you look at a galaxy and you see some object moving around the galaxy, then you find that the gravitational potential is as if there's matter even outside the luminous galaxy. But for that particular thing, for the that I just explained, which is the origin of dark matter, they have given alternative explanations. So that is perhaps not so strong. Then there are other effects, as you mentioned, baryonic acoustic oscillations. There are also models that tend to explain those to some degree. What I think is the hardest is to explain is something called the bullet cluster, which is one observation, but a very good one. So there's basically one galaxy shooting through the other, hence the name bullet. And so you see the gaseous trail of the shot, and so you kind of measure from the result what is the gravitational mass, and therefore you see a lot of dark matter there. And the problem, the thing is that this is very complicated. So it's one system, but it's a very complicated system. So it's very, very difficult to explain with any other model than a model with matter moving around and creating some shape, which gives some gravitational shape. If you think just of modifying the gravitational force or I don't know, some other explanation that doesn't involve dark matter, it's extremely hard to explain this one event. So that is the one that is considered as a nail in the coffin of non-dark matter theories.
I don't know. I wouldn't say the nail, because there are.
No, I mean, yeah, I mean, sure. It's not. People are always looking for. I mean, and it's good. It's good to try to find to find alternatives is just I find it very hard to believe that somebody will come up with a theory that matches that very well. It seems unlikely. I don't know. You can never say no. That's good.
You wouldn't
science,
put your money on.
But yeah, it seems very unlikely.
Horațiu, thank you very much for this evening. Indeed, we went very deep into physics, string theory, and for the people who ask, I don't know if I will redo the lives with Ada and Ciprian. Maybe I will do it. We will see. And before I close, I will ask you, Horațiu, not to close the browser, because we discuss a little bit more about our friends, which we know together, and then see each other. Goodbye.
Right.
Okay, so everybody, thanks for watching. Next time. Bye-bye. Thank you, Horațiu.
Bye. Thank you.